In the next few videos, we're going to be studying theories that can explain the covalent bond. The key word for the covalent bond is that it's a bond formed when there's sharing of electrons. And the two theories that we're going to see are valence bond theory and molecular orbital theory. In this video, we're going to provide a little introduction about valence bond theory. Okay, the main key of, keyword of valence bond theory is that when a bond is formed between two atoms, okay, again, that is due to the sharing of electrons, okay, but that sharing is caused by an overlap of the wave functions of the electrons of the atom. Okay, so let's think about the H2 molecule. And when we think about the H2 molecule in the context of valence bond theory, we can think about the atoms separated without first forming the bond, and then we can understand what are the electronic wave functions of the separated atoms. Okay, we know that the electronic configuration of helium is 1s1, the electronic of hydrogen is 1s1, and the electronic configuration of hydrogen is also 1s1. So when we draw these atoms, we can say that, well, this is how the electronic wave functions look like. Okay, this is your atom HA, there's your atom HB, and each one has an electron. Okay, so when these two atoms come together to form a bond, form the H2 molecule, those two electrons are going to be shared between the two atoms, okay, and the sharing is caused by an overlap of these 1s atomic functions. Okay, so again, that is the 1s, and when you form the molecule, what happens is that there will be your atom HA, HB, and then there's an overlap of these atomic functions, and that means that these two electrons that you have right here, okay, now can be shared by the two atoms, and that is what forms the bond. Okay, so that is kind of in a nutshell the gist of valence bond theory. Now, we're not going to see any quantitative aspects of this theory. We're not going to solve any Schrödinger equation, but we can start to think about how you would write this, the wave function for the molecule or for the bond, not for the individual atoms, okay, in the context of these concepts. Right, so again, the idea would be see what type of shape this wave function for the H2 molecule would look like, or would have. All right, so we know that at this one you have separated atoms. What happens is that the wave function can be written as, well, the wave function of HA having electron 1, okay, and that is what it means. This would mean that the atom HA has electron 1 associated with it. Okay, and then we can actually say that, well, then the other electron should be in the other atom HB. Okay, so that would mean now you have a molecule, and what happens is that, well, one of the electrons belongs to one atom, and the other electron will belong to the other atom, and these wave functions that you have right here will be the 1s orbitals that we know from atomic structure. Okay, but this is rather incomplete, as you can see, because of course when the molecule is formed, it's not true that one electron should belong to one of the atoms and the electron to the other atom. It's quite possible that the second electron belongs to the first atom and the first electron belongs to the second atom. Right, so a much better way to do this would be to say, well, this could be true at any point during the molecule or while the molecule is formed, but then it's also true that you have a situation like this. The second electron now can be characterized by one s wave function that is centered on the first atom, and then the first electron, okay, could be characterized by a 1s wave function that is centered on the p atom. Okay, so now this is actually much more complete than, again, what we actually had initially. What is more, we can even complete this additionally by incorporating other situations. For example, when you have the molecule like this, okay, because the two electrons are being shared by the two atoms, okay, it's quite possible that the two electrons might actually be closer to the A atom than to the B atom, right? And that's something that could possibly happen. It will happen a significant fraction of the time, but if you want to describe the molecule quantitatively and accurately, you actually have to consider situations in which, again, the two electrons might be closer to one of the atoms than the other. A way to do this would be to say, well, we actually have that atom HA has both electrons, okay, HA2. Again, what this means is that you can describe the wave functions of the electrons 1 and 2 as 1s orbitals centered on the A atom, which is another way to say that those two electrons belong to one of the atoms. And additionally, well, if that is true, then the same thing could happen when you actually have that, or for atom B. Okay, so this is also a possibility. Of course, we do understand that these situations are going to be quite rare, right? So those electrons are being shared by the two atoms, and again, it's possible that they can be closer to one of the atoms than the other, but that is going to happen just a fraction of the time, right? So you actually have to correct this by a coefficient lambda, which is going to be quite small, okay? Because again, this only happens just a fraction of the time. Anyway, so this is just to give you an idea for how you would actually describe this bonding situation in which electrons are being shared by the two atoms. But again, to recap what we actually have seen in this video, the main concept of valence bond theory is that bonds are formed by the sharing of electrons, and that sharing is taking place when atomic functions, right, so those 1s orbitals overlap, okay, so that the electrons can be shared by the two atoms.